Hello and welcome. Today we dive into the captivating world of chemistry, exploring reactions between acids and bases. Our journey begins in a world unseen by the naked eye, a world where atoms and molecules engage in a delicate dance of charge and balance, creating the reality we experience every day. So, what exactly are acids and bases? Well, in the simplest terms, acids are substances that can donate a hydrogen ion, also known as a proton, to another substance. Common examples include hydrochloric acid, sulfuric acid, and acetic acid. These might sound familiar as they're often found in laboratories, and in some cases, your kitchen. On the other hand, bases are substances that can accept a hydrogen ion. Sodium hydroxide and ammonia are classic examples, substances that you may have encountered in your cleaning supplies, or even in the creation of homemade pretzels. But why are we so interested in these proton donors and acceptors? It's because they're fundamental to life as we know it. From the food we eat, to the air we breathe, to the very cells in our bodies, acids and bases play a crucial role. They're involved in digestion, respiration, and countless biochemical reactions that keep us alive and well. As we move forward, we'll be working with some of these acids and bases in a series of experiments. We'll observe their reactions, test their acidity or basicity, and try to understand their behavior a little better. But before we do, it's important to remember one thing: safety always comes first. So, make sure to gear up before we begin. It's time for us to roll up our sleeves, don our safety goggles, and dive into the fascinating world of acids and bases. Starting with our acids, hydrochloric acid is up first. This common laboratory acid is known for its strong reactivity. When mixed with water, something fascinating happens. The hydrochloric acid dissociates, breaking down into hydrogen ions and chloride ions. This process is all about the exchange of electrons, which is the heart of many chemical reactions. The resulting solution is highly acidic. This doesn't mean it's similar to your morning orange juice, far from it. In a scientific context, an acidic solution has a high concentration of hydrogen ions. This is measured on a scale known as pH, where lower values indicate higher acidity. The properties of this solution are interesting. It's corrosive, which means it can wear away or destroy materials over time. It's also conductive, thanks to those free ions floating around, making it capable of carrying an electrical current. Sounds quite powerful, doesn't it? Now this might raise a question in your mind. If it's so corrosive and potent, how do chemists handle this stuff safely? Well, the answer lies in dilution. By adding water to the hydrochloric acid, we reduce its concentration, making it safer to handle. But remember, even in a diluted form, it's still an acid and needs to be treated with respect. The reaction of hydrochloric acid with water is a prime example of acid behavior. It's a process that's happening right in front of your eyes in real time. It's not some abstract concept or complex equation, but a tangible, observable phenomenon. This is the magic and allure of chemistry. It's not just about memorizing formulas or crunching numbers. It's about understanding the fundamental processes that shape the world around us, from the food we eat to the air we breathe. There you have it, an acidic solution right in front of your eyes. But our journey doesn't stop here. Up next, we'll be exploring bases and how they behave. So stick around, because the adventure is just getting started. Now, moving on to our bases, we take sodium hydroxide as our example. Sodium hydroxide, also known as lye or caustic soda, is a strong base commonly used in various household products such as drain cleaners and oven cleaners. But what makes it a base, and how does it behave when mixed with water? Let's find out. We begin by adding a small amount of sodium hydroxide to a clean beaker of water. As we mix it in, we can observe some immediate changes. The solution begins to heat up, a phenomenon known as an exothermic reaction. This is because the dissociation of sodium hydroxide in water releases energy in the form of heat. But what's happening on a molecular level? When sodium hydroxide dissolves in water, it breaks down into sodium ions, Na+, and hydroxide ions, OH. These hydroxide ions are what make a solution basic. Now, if we were to taste this solution, which I strongly advise against, it would have a bitter taste, one of the characteristic properties of bases. Another characteristic is its slippery or soapy feel. But again, please don't try this at home. These observations are for educational purposes only, and safety should always be your top priority. When it comes to color change, bases turn red litmus paper blue, another way to identify them. But remember, always handle these substances with care, using gloves and protecting your eyes. So we've seen that our sodium hydroxide solution has heated up. It has a higher concentration of hydroxide ions, and it would feel slippery and taste bitter. We've also learned that it turns red litmus paper blue, and that's how a basic solution looks and behaves. These properties are not just fascinating nuggets of knowledge, they are also crucial in various scientific fields and everyday applications. From understanding how soap cleans to developing effective antacids, the world of bases is indeed a thrilling one to explore. To confirm our results, we'll use a simple yet effective tool: litmus paper. This ingenious invention has been helping scientists determine the pH level of solutions for centuries. To understand how litmus paper works, we need to know a bit about pH. It's a scale that measures how acidic or basic a solution is, ranging from 0 to 14. A pH of 7 is neutral. Anything below 7 is considered acidic, and anything above 7 is basic. Litmus paper is made by treating paper with natural dyes derived from lichens. The color of the treated paper changes in response to the acidity or basicity of the solution it comes into contact with. So, let's put our litmus paper to the test. We'll begin with our acidic solution from earlier. When we dip the litmus paper into the solution, it turns red. This confirms that our solution is indeed acidic, with a pH less than 7. Next, let's test our basic solution. As we dip the litmus paper into this solution, the paper turns blue. This indicates that the pH of the solution is more than 7, confirming its basic nature. Now what if we were to test a neutral solution, like distilled water? Well, the litmus paper would remain unchanged, indicating a pH of around 7. It's important to note that while litmus paper can tell us whether a solution is acidic or basic, it doesn't provide a precise pH value. For that, we would need to use a pH meter or universal indicator. But for a quick and easy test, litmus paper does the job perfectly. It's a staple in laboratories around the world, and for good reason. As you can see, litmus paper gives us a clear indication of whether a solution is acidic or basic. By simply observing the color change, we can gain valuable information about the nature of our solutions. This is not only fascinating, but also crucial in many areas of science and industry. So, what have we learned today? We embarked on a journey into the captivating world of chemistry, specifically exploring the reactions between acids and bases. We started our experiment by introducing our lineup of chemicals: hydrochloric acid, sulfuric acid, and acetic acid, which are all acids. On the other side, we had sodium hydroxide and ammonia, our examples of bases. We then delved into the reactions of these acids and bases when mixed with water. The acids dissociated into their respective ions, creating a highly acidic solution. Similarly, the bases broke down into their constituent ions, resulting in a highly basic solution. These reactions showcase the fundamental characteristics of acids and bases, providing us with a vivid, real-time understanding. To further our understanding, we employed a simple yet effective tool: litmus paper. This humble strip of paper provided us with a visual confirmation of the acidity or basicity of our solutions. Remember how it turned red when dipped into an acidic solution, indicating a low pH? And when it was dipped into a basic solution, it turned blue, signaling a high pH. This practical application of chemistry is not confined to a laboratory setting but holds significance in various scientific and industrial applications. In essence, we unraveled the incredible reactions between acids and bases, witnessed their distinctive behaviors, and learned how to test for acidity and basicity. This exploration has hopefully deepened your understanding and sparked a curiosity for the fascinating world of chemistry. That concludes our journey into the reactions between acids and bases. Remember, the world of chemistry is vast and ever-evolving, and there's always more to learn. So stay curious, keep exploring, and never stop asking questions. Remember to like, share, and subscribe for more chemistry adventures.